here for his second talk. He gave us a talk on Monday. And, Pratik, I had a bit of a conversation also, but anyway, Pratik felt he might want to talk about slightly different things from the talk, his second talk as announced, perhaps more as a connect with the first one. Anyway, so we look forward to this second talk. My request to everyone is, of course, give and take is really why we have these talks, and that's wonderful. We should, of course, do that. But let's keep about an hour and a half in mind, unlike the standard string theory seminars, which will go for 2.5 hours, about an hour and a half till about 12:30 in mind for this talk, because various people have various constraints. And I also request you to keep that rough time frame. Okay, go ahead. Thank you.
Okay, thank you so much. Okay, very good. So what I'll be talking about today is mostly about the relation of randomness with the emergence of spacetime. So this is some theme that I tried to briefly emphasize during the talk on Monday, and I'll try to give you some more details here about how randomness seems to play an important role in this emergence of spacetime. So just to recap what we discussed on Monday, we talked a little bit about the black hole information puzzle and how that can guide us towards quantum gravity. It's a puzzle well within the regime of the effective field theory of GR and quantum field theory, and so we'd like to understand it from a bottom-up perspective, how to make sense of it. And the information puzzle, just to summarize briefly, was really a tension between three things. It was between the principle of unitarity in quantum mechanics, thermodynamics of black holes, namely that they have in some sense a coarse-grained entropy given by the area over 4G, and the equivalence principle of general relativity. So these are almost the basic things of each of these different principles, and that was in tension for the reason that Hawking's calculation relied on the equivalence principle at the horizon, and it concluded that the state that you get out is mixed in conflict with the fact that the coarse-grained entropy of the black hole is going down with time. So one needs to make sense of how the entropy of this region, this box where we've collected all the radiation, goes up for a while but then eventually comes down, which was what we called the page curve. Right? And then I briefly mentioned how these ideas from ADS-CFT, especially the Ryu-Takenagi formula, help you find the page curve. In particular, the entropy of any region is given by a minimization over all possible bulk regions labeled little r, all with the constraint that little r is strictly bigger than your region capital R. And you minimize over this generalized entropy, the thing that Bekenstein thought had an entropic interpretation. So in this particular scenario, what you do is just minimize over all possible I. I is often what's called an island. And there's two contributions. So I is drawn here. So this is some disconnected piece from the radiation that you have. It's something really far away. But nevertheless, we include such a thing and try to minimize over the island for the generalized entropy. And the generalized entropy gets two contributions. There's the standard bulk entropy of the quantum fields in the union of these two regions, plus a contribution that comes from the endpoint of this interval, which is the area of the boundary of A over 4G. Before the page time, so the page curve roughly looks like that. So to start with, the entropy just goes up and there is no island. All you do is compute the semiclassical entropy in the region capital R. That keeps going up for a while, but at some point it's advantageous to include an island, and this island does a good job of minimizing this because the amount of entropy here is really large and it's purified by the stuff that's inside the horizon. So you win in terms of reducing the entropy. It comes at an area cost, and so there's some competition between these things. But since the area of the black hole is going down as a function of time, you win because of that. So it's advantageous post a particular time, the page time, to choose an island. And with this island, you can compute this page curve.
Pratik, in that second graph, what is the x-axis, y-axis? Is that entropy?
This is the fine-grained entropy of the region R as a function of time.
Thank you.
Yeah.
So, if the Ryu-Takenagi formula is the formula to hold, it will hold for all time, or no?
That's right.
Right?
So at early times also it holds, because what happens is at that time it's disadvantageous to include the island because the area cost is bigger. So the area here, so there's two curves. There's the area which is going down as a function of time, and there's the thermal entropy of this gas which is going up as a function of time. And so it's a minimization over those two facts.
So the island shrinks to 0
The island shrinks to 0 at late times, like when the black hole is gone. It's at some finite time, but it shrinks to 0. And that's a region which is a little outside semi-classical control, but we'll actually talk about that today. So, okay, very good. So that was sort of the idea. And then we saw that there's this general theme of how entanglement plays an important role in the emergence of space-time. This is a particular situation where we can see that. The fact that this entanglement, so in the standard Ryuta-Kinagi formula, one basically minimizes roughly over area of a region surrounding the region of interest. But here we just have this completely disconnected region which naively seems like it's very far away. But in terms of entanglement, it becomes advantageous to include it. So there's a sense in which it's sort of close to you because of the presence of this entanglement. Okay, so there's a rough sense in which the role, I mean, in this formula itself, we can see that area is some geometric piece, and then there's some bulk piece which captures entanglement, and they sort of play similar roles. So the, yeah. Yes.
So the curve that's going diagonally down
Yes.
is the first term,
Is the first term.
and the curve that's
It-
going diagonally up is the second term,
Yeah.
and the minimization is on the sum of these two.
Uh,
There's a bracket around the two terms before.
So there's two things we should say. So the two curves, what I'm drawing here, this is just the EFT entropy of the region R. Okay, so just of this region. And this thing is the first term, as you said, the area of this thing over 4G. Right? When you include I, that's almost 0 because almost all the stuff here is purified by that stuff. And so this term is almost 0. So what you're competing is this term on its own versus just the entropy of R without the island. Those are the two things that are competing, and so there's a transition between them.
In terms of the time, the slope is very different.
The slope can be different, yes, it depends on the details of the theory. Yeah.
I guess people are probably not familiar with the language of some entropy purified by some black hole. So maybe that's causing a bit of a confusion. Including
Yeah, well, of course, this language is unfamiliar, but you should go ahead.
Okay, sorry.
The kink is real.
No, the kink is not real actually. I mean, okay, in some approximation, yes, but in a strict limit, yes, but in any realistic system, it'll get smoothed out by some effects. And in fact, these models like the random tensor network and so on help us compute how it gets smoothed out precisely.
I don't want to take you too far aside, but I mean, the page kind of curve is also conceptually similar, right?
Yes.
In that you have two systems with two dimensionalities.
Yes. I'll comment on that. Yeah, it's not just conceptual. It's literally the same.
Yeah, exactly.
Yeah.
So I mean, that might map to things people are more.
Yeah. This was just a broad overview of what I was just saying. Yeah. Okay. Good. So we mentioned how this entanglement played an important role there. So what I'll try to focus on today is a slightly related but different aspect, which is the fact that randomness played an important role. So there were two senses in which this plays an important role, and I'll mention both of them one by one. The first thing we had talked about on Monday was this connection between these random tensor networks and the gravitational path integral. So I'll give you a sort of sketch of how that goes. And there, the randomness in the tensor network was really important to match on to this gravitational path integral, as I'll show you. And then this randomness has an important other avatar, which I'll talk about in the second part, which is related to the fact that these wormholes, these effects in the gravitational path integral, which give you the page curve, are actually in somewhat tension with ADS-CFT. So we'll talk about how we haven't completely resolved the black hole information puzzle for that reason. Okay? So it's a sort of an open question, and how we can sharpen that question.
So the first part, the random tensor networks, that's just some toy one, right? There's randomness in your toy model, but that need not be a physical thing.
So what I'll try to emphasize is the fact that the toy model, which is the random tensor network, has a feature. That feature is also visible precisely in the gravitational path integral in sort of a one-to-one correspondence. And so it's very suggestive that the gravitational path integral also has that same feature. In the random tensor network, you could, I mean, when you do these random averages, it resembles the gravitational path integral very directly, as I'll try to emphasize. And so the point being made is that randomness is also somewhere there in the gravitational path integral calculation. There's other senses in which we will talk about the gravitational path integral containing randomness, but this is one sense in which it's the case.
Or is it that if you're looking for some properties which will be true for a generic system, then if you random average it, it might be a more convenient way to apply.
Exactly. So that's precisely the point. Very often, trying to calculate things using random averages is much more convenient in all sorts of fields, as opposed to computing something for a particular instance. And what I'm trying to emphasize is that it seems like that's what gravity is doing. So the gravity description is often a much simpler description of a more complicated system. And somehow it appears that gravity is also circumventing all this complicatedness of the other system by doing something like a random average. Yeah.
These random averages tend to, because it tends to get rid of all sorts of phase correlations.
Yes.
It tend to give you very classical or very high temperature incandescent matter context, something which is somewhere below the spectrum.
Yeah.
Temperature kind of answer.
Yeah, here it somehow does it in a smarter way where it sort of keeps track of energy, because energy is a conserved quantity here, and so it keeps track of that, but modulo that it does some sort of averaging. I'll try to explain how. Okay, good. So that's sort of the overview. Let me start by talking about this first part, and in order to just sketch what the physics behind this, I'm going to use a model which itself will be relevant for this, which is called JT gravity. This JT gravity is a two-dimensional theory of gravity, which has been used a lot recently, and the presence of randomness there is one of the important points, namely because this is an instance of ADS-CFT where a gravitational theory is not dual to a single Hamiltonian, a single CFT, but instead it's dual to an ensemble of random Hamiltonians. So everything that the gravitational path integral computes is a random average over some set of Hamiltonians weighted in some particular way. Okay? So that in that sense, it's an unusual ADS-CFT duality. So that leads to some tension with traditional ADS-CFT, as we'll talk about later.
So the randomness that will appear, is it a consequence of this being special, or is it expected to be?
Yeah, good. So in this case, the randomness that is going to appear makes perfect sense because there is some random averaging that's being done. The interesting thing that I find is that in the gravitational path integral in higher dimensions, for example, also behaves qualitatively similar. There are effects like wormholes there as well. The page curve is calculated in a very similar way and so on. So even there, those effects are similar, even though we don't understand what kind of random averaging could be happening on the CFT side. So that's really where the tension comes in. But the gravity aspect is still similar. So I'm sort of using this as a guide to understand. Here we understand clearly what's happening, and then we have to question what's happening in other situations.
Okay. Randomness in some sense is kind of a deeper understanding of ADS-CFT.
That's my slogan here. Yeah, I'm hoping that somehow there's something that randomness has to do with emergence of spacetime based on these models, and so we need to understand that. Okay, so I'll only briefly. JT gravity is a subject that's been studied a lot. I'm just going to mention a few things that you need to know in order to understand it. It basically is a very simple theory. It has two fields, which is the metric and a dilaton. And its equations of motion are also very simple, and the solutions are essentially two-sided black holes. With an ADS2 metric and a non-trivial dilaton profile, and they look as follows. I'm just going to draw a Penrose diagram here, which looks like this. Yes.
So I don't understand this statement that randomness emerges space-time.
No, I mean that space-time is somehow, the emergence of space-time is somehow linked to this randomness. The fact that it's in the sense that, there's some complicated system that you're working with, and doing calculations in a complicated system is usually hard. And very often it's a useful trick to do some random averaging to compute that. And what I'm trying to say is there's some sense in which gravity is doing that for the CFT. So the gravitational description, which involves space-time, is somehow coming out from doing some random averaging on the boundary theory. Okay. So here's what the geometries look like. They're basically...
Bulk does not have any random...
no, not necessarily. At least not as far as we can see. Yeah. So there's these. So this is a two-sided black hole. These 45-degree lines are the horizons of this black hole, and I'm drawing a space-like slice through it and labeling it sigma. And the dilaton profile is basically phi is given by phi h square root 1 plus x squared, where x is some coordinate that goes along this direction, and there's some time direction there. Okay. So essentially, if I was to just plot it, it roughly looks like that. Okay. So there's some minimum value which is phi h. This is the dilaton as a function of this. There's some minimum value phi h, and then it just grows towards the boundary and gets cut off at some point. Okay. So this is qualitatively similar to higher dimensional black holes, in that in higher dimensional black holes you have some asymptotic boundary which is a big space, and then as you go towards the black hole there's a horizon at some point, so that's a surface of minimal area, and then you go on to another black hole on the other side. So this phi h plays the role, this point plays the role of the edge of this surface, or in particular it's the a over 4g of this point which will play the role of the coarse-grained entropy. And in this theory there's no, the role of a over 4g is really played by some constant s naught plus 2 pi times the dilaton field. Okay? So it's the value of the dilaton really which measures the amount of entropy that this black hole carries. Now this theory is simple enough that all the solutions are just a one parameter family, and that's about it. Okay, so it's just labeled by one parameter phi h. Okay, good. So now let me talk about the gravitational path integral here. In the gravitational path integral, what we do is compute boundary quantities using the boundary path integral. So for instance, we can define states of the following form. The standard state to define is the thermofield double state, which is defined by a semicircle of length beta over 2. If we want to compute the norm of this state, it's given by a boundary of length beta. It's basically something like trace of e to the minus beta h. It's the thermal partition function. And the rules of ADS-CFT basically say fix those as boundary conditions and fill in everything in the bulk. When you fill this in, what you find is basically a Euclidean version of this. So this is related to this picture I was drawing for the gravitational path integral, namely that there's this cigar-like geometry where you start from the boundary with a circle beta and then it caps off at some point. That's this disk. Okay. And if I choose a particular beta, there's a particular value of phi h given by 2 pi over beta, which is the value at which this solution is smooth. Okay.
The thermofield double states have zero entropy?
Zero entropy meaning entanglement entropy? No, they have basically the thermal entropy, because the thermofield double is a purification of the thermal state, so it has a thermal entropy. Yeah. Good. So this is the standard description of the gravitational path integral. Now in order to relate this to random tensor networks, I'm going to use a particular basis that is useful. And this basis is one which I call the fixed geometry or fixed area basis. And the basis looks as follows. For any boundary conditions that I set, beta over 2, I can specify on some sigma the data, which is the dilaton value phi of x, and say the normal derivative of phi being 0. Okay. So this is a consistent variational principle where I specify some boundary conditions now in the bulk, which is the new thing here, instead of specifying it just on the boundary, and then fill this in with whatever solution is consistent with these boundary conditions. Okay. When you do that, the solutions are actually pretty simple, and this basis is what I'm going to call the phi of x basis.
You're specifying two pieces of data on that slide?
Yeah.
So and you're specifying normalizability on this thing?
This thing is the standard beta over, like, yeah, normalizability. Yeah.
So is that too much then? It feels like you should surround it by one piece of data.
This is playing the role of the other beta, roughly speaking.
So if you had phi of x, I understand.
But there's two fields, right? So there's G and phi. So here in this, there's G. So, okay. So there's the induced metric, GUU, and that's conjugate to this d phi. And then there's phi, which is conjugate to the extrinsic curvature. So you can specify any two of them.
Yeah.
And the normal direction is the radial direction?
No, the normal direction is the time direction. So you want to choose it. I want to basically choose it so that it's on the slice of time symmetry, basically. Okay.
So does this data also pick out for you what the sigma should be?
Yes. I mean, yes. It picks out that sigma, basically. I mean, let me just say what the solutions are, and then we can talk about that. So the solutions to this are pretty simple. The solutions. So if I want to compute, say, so we can think about the following thing. We can compute, we can write down psi as a superposition over this basis. Firstly, I can specify phi of x arbitrarily, but it's going to turn out in this simple theory that everything else is fixed by constraint equations. The only thing I get to specify is really phi h, because it's all only specified by one parameter. So all that's going to be is just a number, and that number is basically the value at the minimum on this slice.
Okay. So you cannot specify an arbitrary function.
If you specify an arbitrary function, you'll get the answer 0, basically. Those are just null states.
Meaning there's no solution.
Yeah, that's right.
No solution to the classical.
Yeah, that's right.
So it was too much data to specify.
Yes, I mean, formally speaking, it's, yeah, that's right. That's because we didn't account for the constraint equations at that point.
Sure.
Yeah, that's right. Yes. Good. Okay. So now good. Okay, so this just becomes.
You are not going to require k equal to 0.
No, I cannot require that simultaneously. Yeah. And we'll see that the solutions won't necessarily have k equals 0. So we have a sum over phi h, psi of phi h, times the state phi h. Okay. Good. Now, this is basically all I've done is inserted a complete set of states, right? So this is the same as just the sum over phi h, psi, where this phi h psi is computed by this problem. This problem basically computes the overlap between the state psi, which was defined by asymptotic boundary conditions, and this bulk state phi h, which is defined by this bulk boundary condition.
And you have a discrete spectrum of phi h?
No, it's actually continuous.
But you're just
Yeah.
writing it as a sum?
Yeah, just roughly. Yeah. Okay.
Let me just take a minute. Gagan and Rajesh in particular, sorry I can't see you on the screen because we are using the blackboard. So please just interrupt if you have any clarifications and ask them as we go along. Thank you.
Sure.
So this thing has some action, which is just, so let's call this solution G phi h. It has some action, and all we are saying is this amplitude, the amplitude in this particular basis is just given by e to the minus that action. Good. Now the solutions are as follows. As we saw, there were basically just a one parameter family of solutions, so we can just specify some values of phi h. And there's a special value of phi h for a given beta where this thing becomes smooth. For any other value, there's basically going to be a conical defect at the center. Okay, so the solutions will look like this. They'll have some kink there, still beta over 2, and in this particular solution, there'll be a particular value of phi h there. So generic solutions look like that.
Sorry, I missed something. So,
Yes.
So for a generic phi of x, given that you're setting e and phi also to 0,
Yes.
you won't find any solution.
Yeah.
And when you are expanding in the spaces, you are then therefore only taking those phi of x's which are
Right, and that's why I'm labeling it just by one parameter, which is just phi h. That's right. Yes.
Question on the thermofield double.
Yeah.
In your idea of the sort of information paradox,
Yeah.
both the two low entanglement states which you were not being able to capture within your classical theory was not giving you the correct answer. Maybe one it was not, definitely the other one. How are you going to capture them through a thermofield double, which always has a very high entanglement?
Right. So
Reasonably high entanglement.
So let me say something just to clarify it. Right now, I'm saying something which is a little bit independent of the page curve calculation per se. I'm just trying to emphasize the RT formula part. The RT formula is much more generic, right? Page curve is a special example where we use it. So this is a particular example where I can apply it to the thermofield double state. There it has a particular entropy which is given by the thermal entropy, and we can try to understand that. Yeah.
So this is a kinky solution.
This is a kinky solution. Yes. Yes, Rajesh. Oh, sorry.
Yeah. No, just to make sure I understand, you're saying that you specify some state psi on this semicircular arc.
Yes.
And then you this factor, this amplitude is the e to the minus the classical action.
Yes.
With that, and on the other, on the diameter, you specify phi h. There's a saddle point. You're saying that you evaluate the action on, but then this conical defect is the only saddle point is typically the one with the conical sort of geometry that you showed. Is that what you're saying?
Yes.
That if I specify this phi as a smooth on the smooth slice, that's not a solution. You won't have a solution if I specify phi h for.
So what I'm saying is that, so I have a one parameter family phi h, and for generic values of phi h, as you said, there's going to be a conical defect on the slice that satisfies these boundary conditions. So if I want to look for a slice which satisfies d phi equals 0 and has the particular profile, you're going to find, the only solution you'll find is this kinky solution.
Okay, so unless phi h is 2 pi over beta.
Exactly. So there's one particular value where that conical defect goes away, but for every other value you find some defect. It's in one-to-one correspondence with that.
Basically the disk type solution where you are making it upper and higher and higher.
Exactly, it's exactly that. So since we saw that all solutions were basically these disk solutions with some values of phi h, every value of phi h would, if it were to be smooth, would correspond to some beta. Now we fixed beta here. So all we can do is pick some slice of this, and that basically looks like this. Yeah.
So here I might have missed this.
Yes.
Is there easy way to see whether this phi h basis is orthonormal in some sense?
Yeah, basically if I take, so all I'm doing is inserting a complete set of states, right? So what I was doing here, essentially if I have some phi profile here and phi prime, I can't patch them together, so there's no overlap between them. Like the rules will be basically take this boundary condition, take that boundary condition, try to put it together, and you can't. Very good. Okay, so that's sort of the picture, and essentially the intuition here is that this state has some distribution. Okay, so the thermal state has some distribution. In fact, in this theory, it ends up being the case that the energy is basically given by phi h squared over 2, because the energy has a continuous spectrum, and it is very directly related to this phi h basis. Okay. So roughly speaking, what we're doing is basically just doing an energy eigenbasis decomposition in this simple example, just an energy eigenbasis decomposition of the thermofield double state, which we know has some spectrum, which looks roughly speaking like that as a function of energy, let's say the weight as a function of psi of E as a function of E. Sorry? Yeah, it's basically this e to the minus I of, sorry?
E to the power minus I g for that particular value.
Yeah. So psi of phi h, which is e to the minus I of g phi h. That's this, and e is just phi h squared by 2. So as a function of phi.
Peak at 2 pi by beta?
That's correct. That's exactly. So what the gravitational path integral is doing is basically finding that peak, right? But instead what we can do is just do it.
Why can't this conical singularity be inverse?
It can. I just drew it that way.
So that would be the dominant one, right?
Uh,
that is less area. Midless volume.
but it also has less weight. Like it's like the competition between Boltzmann factor and entropy. So there's a fall off in energy because of the Boltzmann factor that's given by the action, but there's also a growth because of the entropy, and there'll be some balance between them which is given by this 2 pi over beta. On one side you're losing because of the entropy, and on one side you're losing because of the Boltzmann weight. Okay, and exactly, so this will correspond to the value where phi h is 2 pi over beta. Okay, so all we're doing in this thing is just decomposing into some appropriate basis where we're splitting the calculation into chunks. These chunks all have these solutions which have these conical defects, but then eventually we find, when we integrate over all of them, we find the smooth solution. Okay, so how is this connected to the random tensor network? Okay, so let's model JT gravity using a random tensor network. So it looks as follows. You'll just take a chain of random tensors. Okay, I'm just going to draw a few. Yes.
Literally took a ground state and I took beta to 0,
Yes.
to infinity, then
Yes.
I will see something just rising up near a singularity near equal to.
Yeah, that is a little subtle because this spectrum actually has it goes to 0 eventually at some point.
So that's what I was going to ask,
Yeah.
whether it goes up or
Yeah, so that at that point this semi-classical calculation can't even be trusted. Quantum corrections become important, so you can't even trust that calculation.
So one question. When you do psi norm,
Yes,
right?
yes,
So I take that decomposition,
Yes.
put psi on the left.
yes,
And then I have gluing of these conical
yes,
guys,
yes.
which is not quite just the disk, right?
It's the disk with a conical defect. So
Yeah, but you have to integrate over all these things.
that's right. So let me just write.
But isn't that supposed to be just the disk?
So let me just write that up. Write down what you're saying. So there's psi is just given by sum over phi h mod psi of phi h squared, right? Good. And
So you do saddle point.
you do saddle point over phi h. So that's what was being commented on. This point is where phi becomes 2 pi over beta. Saddle point in that sum becomes. So you're just breaking that calculation into pieces where these conical defects contribute. Eventually you care about that
No,
answer.
but just following up on that, I mean, the fluctuations around the saddle point
Yes.
are fluctuations that create this conical deficit.
Yes.
Is that somehow a familiar rule?
Familiar. I mean,
Normally we look at smooth
Yeah,
fluctuations.
right. Yeah.
so there's certainly energy fluctuations in the state, right? Like in the thermofield double state, there's energy fluctuations, and correspondingly there are also area fluctuations. And this thing is capturing basically the area fluctuations.
In n equals 4 angles, if I were to do something similar,
Yes, yes.
wouldn't the fluctuations just be smooth geometries?
Not necessarily. Depends on what you're computing. I mean, you could treat.
I'm computing
Okay.
partition function.
You can compute the partition function. I'm saying the variable that we're looking at here is the area of the horizon. That variable, I mean, in n equals 4, I mean, here it's a little simple because we don't have matter. When you introduce matter, you need to put in a cutoff, right, in order to make sense of A over 4g. Once you do that, then the fluctuations of that observable are controlled by these conical defects.
I guess the slightly confusing thing is,
Yes.
of course, quantum fluctuations. Suppose I specify the beta on the boundary.
Yes.
Quantum fluctuations, of course, would include everything. Right?
Yes, yes.
But if you were solving classical equations, you would keep smooth geometries subject to that boundary condition.
Yes,
right?
yes.
And here you seem to be deducing from classical saddle points
Yes.
these weights,
Yes.
right? So it's a classical calculation.
Yes, this thing is a classical calculation.
And so you're not including quantum fluctuations.
I mean, yes, in
And
this
yet you are able to-
approximation, yes.
And yet you are able to, so if we were just doing classical calculation, we would ensure smoothness inside given boundary conditions, right? But here you are including these defects. I think, is that part of, Shiraz, what you were asking, at least in my mind?
I think it's part of it. I mean, either I would go completely off shell and then retain only smooth configurations, because smooth configurations are the ones that usually, at least in normal situations, have good action.
You mean in doing the full calculation? Because there's one loop, there's fluctuations around that saddle.
Fluctuations around the
And so
saddle.
this is going to account for like small conical defect fluctuations around the
That's
saddle.
what I thought.
But I mean, in normal situations, we look at fluctuations of the let's say, the graviton, right?
Yes.
The graviton has smooth solutions.
Yes, yes.
And you look at the determinant of those, over those smooth solutions.
Yeah, so that's in a particular limit, I think. So here what we're doing, in order to make sense of this calculation, as we were saying, we need to put in some cutoff, right? So when you're putting in this cutoff, in some sense, you're excising, I mean, you're treating the region around the conical defect as within your cutoff zone. So in that, you're allowed some wiggle room.
Let's not make that point to be special at all, right? I mean, just fluctuate this geometry as if you don't know anything about conical defect. Just fluctuate that.
Yes.
And then that would be the right, I mean, the usual type of path integration.
That's the usual calculation. That's right. That's right. That's right.
Here it's somehow you are making half classical, half quantum kind of thing, where you are computing these quote quantum off-shell configurations using a classical prescription, and that's why you are kind of led to that particular class of quote off-shell, which actually came from an on-shell calculation in some sense.
I mean, in that on-shell calculation, if I added in this projector onto values of the area, then it becomes off-shell in your sense, right? Because I mean, it's a boundary condition in the bulk. Right? I mean, since I'm specifying what the area is in the bulk, I don't have Einstein's equation corresponding to that variable, right? I've removed one component of Einstein's equations. So I'm allowed to have conical defects because of that boundary condition. In the end, of course, I'm integrating that out, so it's the same thing. But this is just an intermediate point where I'm breaking the calculation into that piece.
Yeah. It seems, that's what I would say, that if I were to phrase it in terms of classical solutions, you are thinking of the path integral with a constraint over which you will integrate.
Exactly.
Right? If
exactly.
I'm right. So the constraint probably for any beta, let's say I specify, the constraint is that phi h at the center or whatever takes some value.
That's right.
Now, then you find saddle points with that constraint, which is what you're writing down. And in the back of your mind, ultimately you will integrate over that constraint so that you're doing the original problem.
That's right. That's right. And when you do that, you find basically the same smooth solution.
But just get clarity on that. I mean, when you go and hit actually the smooth disk, as Vijay was asking, that's the classical solution for the partition function.
Yes.
So will there be any consequence of fluctuations away from that?
Of
not being right.
Here, for example,
in the end, going to get just the disk, that's fine.
No. For example, the width of this is computed by this calculation.
And will there be something physical about?
It is the fluctuations either in the energy or in the value of the area. Like if I were to measure the area, say many times, there'll be some fluctuations in the variance of that area will have some value, and this width will compute that variance.
Fluctuations at largen itself?
At largen. I mean, basically, there's an exponential fall off in n. I mean, basically, this width in general situations ends up being of order square root g. Like if you're measuring area, then the delta A basically is order square root g, and this will capture that effect. Area of the horizon.
But there is an off-shell configuration. What do you call a horizon? If it is, in order to define area,
we're integrating over, I mean, we have a clear meaning for what these states are, right? So in all of these states, we have a sigma which has a phi h, and we know what phi h means. So we're integrating over that parameter.
No, but an off-shell configuration.
I'm only integrating over these, right? So I did it partly. It's a constrained instanton-like thing.
Constraint, yeah, exactly.
So with that one constraint,
for that is what I want to understand. With this constraint path integral, then it would not be a complete set of states, right?
Why?
Constraint path integral.
No, it's just a basis. Like constraint. I mean, the phi h is a complete basis of all states. Like we know in JT gravity what are the states. The states are just labeled by this one parameter. So I can always use that basis. This is just, I mean, what you were interested in doing was compute psi. I'm just doing that by inserting this complete set of states in the middle. Each term need not satisfy this smoothness condition. Each term in that could just have some other interpretation. That's given by this kinky saddle. But then in the end, it's the same answer.
Just tell me one more thing, if I may, which
Yes.
is in terms of the constraint you're imposing,
Yes.
how do you specify in a gauge invariant way
Yes.
where that kink is? Because you're going to
Yeah.
specify the value of phi h
Yeah.
at some point.
Yeah, in this it's gauge invariant because what we've specified was dn phi is 0, so it's already extremal in the other direction. And then we've specified phi of x, right? And finding the minimum on a particular slice is some gauge invariant statement. So you just, in each slice, you just look for the minimum value, that's phi h.
So on that boundary slice which has a kink,
Yeah.
the minimum value
It will end up being there, yeah. If you just check what it is, it will end up being there. Because it satisfies that, the behavior of the dilaton where it grows on both directions.
It ends up being at the kink, but what you're specifying in the constraint is that along that boundary
Phi
slice
of x.
is the minimum value.
Yeah, yeah. Yeah.
Sorry, Pratik.
Yes.
Just to add, this width that you are talking of, or this distribution in general,
Yes.
in the dual SYK or whatever
Yes,
the
yes.
random ensemble that
Yes.
you're considering, what would it correspond to? Is it the width of the averaging in the random ensemble?
No, this is, I think, true already without averaging. So what's going to happen is, so in any situation, so in this simple example, because energy is just related to phi h squared, we can just look at the density matrix in the n equals 4 or whatever your favorite CFT is without averaging. That will take some form which looks basically like this Gaussian, and I mean this is just the eigenvalues of the thermal density matrix, and all I'm characterizing is the width of that. So it's going to be that variance. It's the variance already there in the thermofield double state.
Okay.
Does that?
So you're saying this has nothing to do with the ensemble average?
No, like even in n equals 4, like if I look at the energy spectrum, it'll have some fluctuations, right? Like the energy is not definitely equal to the value of the black hole, the one given by the black hole. There's small fluctuations around it, which are 1 over n suppressed, and that's why it's g suppressed here. But nevertheless, there are some fluctuations. So if you wanted to compute something like the energy 2-point function and so on, then you would see this.
Okay.
But the only difference there is we're talking about the area as opposed to the energy, and it's not 100% clear what the boundary dual of the area, so what exactly I would compute. In this simple example, area is just energy, so it doesn't matter. We can just compute energy and we'll get the same answer.
Of course. Please go ahead.
So if I think of this as a basis transformation, presumably some sort of a singular basis transformation, at least in terms of the effects that you are putting in.
Yes.
I mean, normally, of course, I can do it, and partition functions should remain invariant. But partition functions calculated within saddle points don't need to be invariant. And we know in condensed matter often that in 1 degree of freedom, if I did it, saddle points might be good and controlled. But if I did some very complicated transformation in that, a saddle point may not be good.
Yeah.
So here are you assuming, or
No, it's by construction. You can check that. Yeah, you can check that you get the exact same saddle.
Point.
Yeah, basically the saddle point equations of this will end up being the fact that conical defect is not there. There's no conical defect in the solution. Yeah.
One question.
Yes.
I'm informed.
No, please.
Forgive me if that's the case. So, is there like a kind of a phase transition, first order type phase transition being thought of when you go from one saddle point to another as you cross the page curve?
So again, just to emphasize, I'm not talking about the page curve right now. Yeah. So here there isn't going to be a transition. Here, as we vary beta, the energy and correspondingly entropy just changes smoothly, because this peak will shift, like just in standard thermodynamics, it will just shift smoothly. That's all that's going to happen.
So maybe we go ahead from this one.
Yes, please.
For any beta, that what you are doing,
In JT gravity, yes.
even in the very low beta.
Okay, that's in low beta is good. Low beta is like even better. Large beta is the problem. Yeah. Large beta is the problem, as Rajdeep was also asking. That's where quantum corrections become important, and so you have to be a little careful about this. But you can do it with quantum corrections.
And any type of random distribution.
Any type of random distribution. I haven't used a random distribution at this point. You mean the randomness in the ensemble of JT gravity? That's a fixed randomness. So the ensemble, like the ensemble of Hamiltonians dual to JT gravity, has some very particular potential. So it has some fixed thing. If you change that, then you'll change the bulk theory itself. So there's some correspondence between the randomness on the boundary and the bulk theory, and the outcome in the bulk theory. Yeah, generically it will get changed. Yeah, like the spectrum will change, and so it will change all of this. The spectrum is very dense here actually. So there's this parameter, as I was saying, A over 4G is given by this S naught plus 2 pi phi. That S naught parameter is big. So the density of eigenvalues is actually e to the minus S naught. They're e to the minus S naught space. They're very tiny. So it's a very dense spectrum. And that's why, I mean, in this, you see this thing as a continuous approximation. It's because you're not seeing those gaps. Just like in thermodynamics.
So maybe we go ahead.
Okay.
And we can come back to it.
Good. So now let me talk about what the random tensor network picture for this thing is. Okay, so I'm modeling JT gravity with some chain, right? So it's a 1D thing. So I'm thinking of this as sigma. Okay, there's some variance there's some profile for the dilaton, which we said was this phi h times square root of 1 plus x squared, and I'm modeling that by these bonds. Okay, so each bond here, the total bond dimension log d is basically given by a over 4g. Okay, or in this case S naught plus 2 pi phi. Okay. So as phi varies, so there's a minimum value which you should think of as the horizon, and then I'm modeling it in some discrete way, which is arbitrary, as a tensor network which has growing bond dimensions in both directions. Okay, so that's modeling the fact that the dilaton profile looks like that. And now we can try to do the calculation in this. The fact that I took a few tensors is arbitrary.
Dimension means number of bonds?
Yeah, I mean, so there is some dimension associated with that bond, like if it's a qubit it would be 2, but there's some large d qubit there's a bell pair of large d there, and then there's also some number of bonds. This is just representative to say the total bond dimension is changing in this particular.
And then the in-between point with one link. So
that's going to be the horizon.
Phi h.
That's phi h, yeah, that's right. Okay.
JT gravity, is there a calculation which will tell you that not the center but somewhere else is the entanglement entropy, so that this picture kind of has some footing?
This picture has some?
So this is just a model, right? But in order to understand this bond dimension as the value of dilaton, it would have been nice if there is a calculation which you ask about some entanglement entropy and it cuts there, not in the middle, on the left, and you see that is there.
Yes. So that's related a little bit to this.
If it is too far off.
Yeah, I'll mention it briefly. We can talk about it offline. Yeah. Okay. Yes.
Very quickly.
Yes.
When, like in your last talk, when you showed the slide, you had the whole bulk was being kind of modeled by a sort of a 2D random tensor network. But here I understand you're looking at a slice, but you're thinking of it as sort of a slice of the whole tensor, 2D tensor network, a kind of thing?
The thing that I was drawing as a 2D tensor network was basically if we were in higher dimensions. So if we were in ADS 3, then the slice would have been hyperbolic, like 2D hyperbolic space. So that was the thing I was drawing yesterday, which would have been related to a 1 plus 1 CFT.
The time part of it. The time part is...
Yeah, the time part is neglected in all of this. It's always just drawing a spatial slice of it. So I'm just drawing sigma.
Okay.
Good. So in this, and then there's some choice of tensors here, T1, T2, T3, and so on. And all of these tensors are chosen randomly. Randomly meaning that any tensor, it has some number of legs, can be thought of as being acted on by a unitary, or obtained by acting on a unitary on some fixed state 0. Okay, so all I'm doing is taking some reference state, acting with a Haar random unitary, and that outputs some random state, and that's the thing I'm using as this random tensor. Okay, for this thing, we want to compute the entropy just to see the connection with the gravitational path integral, and so you can the standard way to do this. Yeah.
This will give you a vector normally, and then you are.
Yeah, then I will turn it around like.
The standard techniques to get it into a.
Yeah, exactly. So this, for example, this tensor will actually be a 5-party random state, and then 2 of them I'll push to the right. Okay. So in order to compute the entropy, the standard trick is the replica trick, which tries to compute the following quantity. Okay. So let's say we're interested in so there's a left and right. Let's say we're interested in the entropy of the right. Okay. Then for a choice of random tensors, it's really hard to compute it, right? You would have to do some numerics, or so. There's no easy analytic trick to compute this for a particular choice of tensor network, and that's representing the fact that the boundary state is actually complicated. Right? The fact that it's not easy to compute the entropy of a particular member to infinite precision. But on the other hand, what we can do is average. So we can do this average over trace rho to the n, and in this limit, it's going to be a self-averaging quantity. So this is a good approximation for that thing that we would have wanted to compute for a single instance. Okay.
Did you you already motivate the randomness, or you will do it later?
This is at this point it's a choice. The motivation will come from the fact that this will match gravity.
You are not connecting it to that.
I haven't yet connected it to that. Yeah.
And you're going to average the trace row to the power.
Yes, that's also important. Like it's really hard to do the average with the log, but you can check in this regime that it doesn't matter. That average can also be exchanged. That's a more complicated calculation which can also be done with gravity, but it's really subtle. In fact, that's the thing I was otherwise going to talk about. And there are situations where you have to be careful about that fact, but this is not that situation. So here it's fine to exchange this and just.
This matters a lot in disordered systems.
That's right. So
the log or not.
Here
what allows you to.
Yeah, so here it will again become very important at low temperature. So if you try to do the low temperature calculation, it will matter whether you compute the quenched quantity or the annealed quantity. But here in this regime, it doesn't matter because there's a large number of states.
So
Annealed,
yeah,
exactly. Annealed is approximately quenched. Okay, so this thing is the real thing that we compute in gravity, and here because of this random averaging, there's basically a simple fact that average over these random unitaries is basically a sum over permutations. Okay, and so I'm skipping some steps here, but this entropy calculation, this log trace rho r to the n calculation, or in particular the trace rho n to the n calculation, is basically given by a partition function of an Ising-like model with spins living in the group, symmetric group n, which is basically the group formed by all the permutations, and boundary conditions which are set by the calculation that we were trying to do. So since we were computing trace rho to the n, the left boundary condition will be to set it to the identity, which is because we're just doing a standard trace. And on the right, we're going to apply a cyclic permutation because we're trying to compute this product, right? So we're multiplying n matrices, and so that's implemented by doing a cyclic twist. Okay.
Just to make 100% sure I
Yes.
understand. So you have some random tensor network.
Yes.
You have the state on the left, and you push it through, and you have some state on the right.
Yes.
You trace over the state on the left, you get a density matrix for the state on the right.
Yes.
And you take its nth power.
Yes.
And then you compute by doing some averaging in your.
That's right. Yeah.
what's going on.
That's right. That's right. And so the picture looks as follows.
In the Ising model, there is no randomness, right?
No, there isn't.
So, but
The Ising model is the outcome of the randomness. When we do the random average in the tensor network, it becomes an Ising model. So let me just say what it looks like. So we have a boundary condition, which is the identity. So we had all of these tensors. So what it's going to look like is there's some bonds here, and then there's some G1, G2, G3, G4, etc. Okay. So there's some choice of spins, which I'm labeling G, at each point. And it's like an Ising model in the sense there's an advantage for them to align with each other, but you have to keep track of the fact that it becomes cyclic at some point. Okay, let's say G5, G6, whatever. So the boundary conditions on the other side don't agree with each other. So there's going to be a domain wall somewhere, right? So this random averaging gives you a sum over locations of the domain wall. So the domain wall can sit here or here or here. The optimal place for it to sit, of course, is here.
So is it that, just so I understand that mapping to Ising model, is it that you have all these legs of the tensor at L?
Yeah.
You are effectively able to replace that with one Ising variable, or no?
Yeah. So all the vertices, all the random tensors are replaced by a random variable, basically because each of the tensors involves a unitary. You are integrating over these unitaries, and the outcome of that is a sum over permutations. So it replaces the element there by a permutation, and the physical interpretation will become clear in gravity. Okay, I'll just say because it's the same thing. Okay. So.
And what does the bond by the
Sorry, when you say it's the spin is taking values in the symmetric group, you mean it's an element of the symmetric group? It's
Correct.
a group element?
Correct.
But the
Correct.
group element doesn't necessarily square to 1 or anything. So
No.
it's not icing in that sense.
No. Icing just meant like the only thing about icing about it is the fact that the interaction between neighboring vertices is ferromagnetic in the sense that there's a distance measure called the Cayley distance on the group elements, and all it's trying to do is minimize that distance. Yeah.
Sorry, just so I'm very clear. Let's say you're the left with 5 or whatever tensors.
Yeah.
So your 5 indices there.
Yeah.
And when you do group averaging, you contract them,
Yeah.
etc. Is it that each of those 5 indices is replaced by a icing like variable, or?
Yeah, so what will happen is, so there's all of these legs, right?
Yes, yes.
Once you do the Haar averaging, the
Yes.
tensor is just gone, right? Like it's just
Yes.
gone.
Yes.
All you're dictated to do is decide how you're going to glue these legs together.
Yes,
So that's
yes.
dictated by the permutation.
Yes.
But then there's a tension sometimes because here like all of these legs, these 3 legs and these 4 legs, they all consist of the same tensor, therefore the same tensor. So what you're trying to do is glue these legs assigned by the same permutation, which may not agree with the permutation here. That's where the icing cost comes from, the fact that these are not glued in the same way. Okay.
So it's like, roughly the intuition is that so in the partition function, the leading term would be the one in which there's the smallest energy, and the energy or like the smallest contribution comes from roughly the difference between these two permutation. Like
Yes. So we're going to work in a limit where the log of the dimension is taken to be large. So the gap there's a unique ground state and there's a large gap to anything after that.
And so there's a way to see that in like for when n equals 2, it's that's the only option. But
Yeah. Yeah, you can prove this. Yeah, it's provable that the dominant solution will be given by a domain wall at the minimum location, and that in this limit, and that it's basically just cyclic and identity. That's the only thing.
And sorry, I missed what was capital G? Capital G in your.
CN.
Oh, this is CN. Sorry. This is Cn, so it's the cyclic permutation on the n elements because we're implementing this trace row to the n, which is basically implemented by the cyclic twist.
Okay, and and that is that's the boundary between the left and the right pieces that you listing. Is that what's?
Yeah, so it's the boundary condition. So there's 2 boundaries. There's a boundary on the left where we're implementing this boundary condition being identity, and then there's the boundary on the right where the boundary condition is being implemented to be the cyclic one, and then we're filling in the bulk with those boundary conditions.
Yeah, but in the language of your sigma, this
Oh.
is where you're chopping off.
Good.
Sigma.
Let me just say what it means in the language of sigma. Yeah, this is basically where I'm chopping off sigma. That's correct. Yeah. Yeah. So now let's just relate this to the gravity calculation. The gravity calculation was as follows. Now the way I want to interpret this is each random tensor network is a phi h state. Okay, so remember that there was this basis of states which was labeled by phi h, and since the tensor network clearly knows about this bond dimensions, there's some value of phi h that this corresponds to. I could have picked some different values of phi h, and then it would be a different tensor network with different number of bonds. Yeah.
Somehow this unitary group and symmetry groups are interlinked.
Yeah. This is basically a thing called Weingarten calculus. Like there's a direct connection between them. Yeah, I don't want to go into those details. Okay. So now let's look at the gravity picture for this. The gravity picture is as follows. So for any given phi h, we saw that there was this sort of a solution where we just specify the value of phi, and there's a conical defect here. So now what we're trying to do is take 2 of these. That gives us a density matrix. Okay, and then we're taking 2 copies of this. So this is basically trying to compute trace rho r squared. The way to compute trace rho r squared is we glue the left copies with each other. Right? So related to Rajesh's question, this is basically where sigma ends, and the boundary condition is implementing the fact that the left ends are glued together. On the other hand, the right end is glued that way. Okay? And then you want to fill in what the bulk solution is. And the bulk solution is as follows. Now we have an option to choose where the replication will happen. Okay? So we can choose some point here, so that we glue everything to the left of it, okay, and then everything on the right of it is glued cyclically. Okay, so this is basically mirroring the fact that in the tensor network, we just chose a domain wall and then everything to the right was the cyclic permutation, everything to the left was the identity permutation. That's basically the fact that these spins are basically the gluing in the bulk. Okay, so that's really where this is coming in. And then you're going to optimize over the location. Yes?
Sorry. And now we are describing the gravity calculation.
Yes.
Right, so you're saying you have these wedges and now this to compute trace rho square.
Yes.
This is what you do.
Yes, that's right. And the reason this is allowed is because we specified phi, right? So the usual issue with things like this is the fact that there'll be a conical defect when we replicate around a random point. But since we specified phi, there's no conjugate equation which specifies smoothness there. So we've sort of relaxed one of Einstein's equations, and this solution where we glue at an arbitrary point is a valid solution to the boundary conditions we chose. Given that, we can optimize where this location of this domain wall is, and you'll find that it sits at basically the minimum location, just like it does in the random tensor network. Okay? So that's the concrete sense in which these phi h states more generally are dual to these random tensor networks. And then going back, we can remember that when we computed what we were using was this basis, right? So there was a phi h sum, psi of phi h, okay? And then we can try to compute trace rho to the n, right? And trace rho to the n is approximately given in some approximation by a sum over phi mod psi of phi to the 2n e to the minus n minus 1 a over 4g. This is basically the answer that comes from a fixed tensor network, or here let me call it s of phi. This is a function of phi. So the answer from a fixed tensor network, which is labeled by a value of phi, is given by this thing. And then there's some weights that it comes along with. This exactly matches the fact that in the gravitational path integral, each of these pieces, so this piece is a psi of phi, this piece is a psi of phi, this piece is a psi star of phi, and this piece is a psi star of phi. Right? So this thing is coming exactly from the bulk action of these regions. And this piece just comes from the replication in the standard way as in the random tensor network.
So in this gluing also there is no randomness, there may be permutation.
So now the point is what we did on the in the tensor network was there was some random averaging that was done to get to the gluing point, right? To get to the permutation spin model. That step involved randomness. In gravity, we don't know what we did. We just used this gravitational path integral with in some basis to compute this thing. But what I'm saying is it's very suggestive that there's some, the pattern is exactly the same. In the spin model, we had this sum over permutations, and in the gravitational path integral, we have this sum over gluings, which basically mirror each other. Okay.
Averaging is there in the gravity.
It's suggestive of some sort of coarse graining that's hidden in the fact that we're doing this. That's right.
Speaking about gravity, couldn't I have done it for any something where I go to high enough temperature and say a saddle point is valid? Would I have been? I mean, it not look like a conical defect.
Yeah, that's the thing that's suggestive. You can always do a saddle point. I mean, if you have some parameter.
Saddle points here or saddle points there.
So that's fine. That's fine. Here, the extra thing that's being done is the suggestive fact that it's exactly related to this model, and the bulk is also doing it via this sum over gluings. Okay.
But this analog of the Ising spins, is there something you want to identify in the box?
Yeah. So what I want to identify is the fact that when I define this sigma state, like the fixed dilaton state, on that state there's many locations, and essentially we're thinking about it. I mean, every there's a set of class of geometries we're integrating over, where we're basically assigning how these different sigmas are glued to each other, and at each point I can basically assign a variable which is a permutation, roughly speaking, and then glue these different sigmas in various ways. That is the analog. The pattern of gluing is the analog of these Ising spins.
But you're not, I thought the gluing was just, like on the right hand side picture, the gluing is just of these edges directly with each other, right? So you're not permuting them individually at every point. you're not permuting the sheets.
Yeah, so here's something I could have done. So what I was saying was, so the fact that we glued the left ends and the right ends together was the fact that there was a boundary condition. That's analogous to the fact that we had identity and cyclic here. But after that, there was a choice of this location. Right? I chose some location around which to the left of it I was gluing trivially, and to the right of it I was gluing in this cyclic way. I could have also chosen other permutations. I mean, in this simple case there's only the identity and the swap, but if I had n equals a higher n, we could have chosen different permutations. All of those would be valid solutions to the problem we started with, in the sense that all of them satisfy the fixed phi and dn phi boundary conditions as well as the asymptotic boundary conditions.
Okay, but that's still at one point at the end, right? I am a little puzzled about all the G1, G2, G3 that you have in the middle before that.
Yeah. So it's not just at the boundary. It's also at this point. So okay, let me choose two different points just to make this clear.
That's the point associated with the CN.
No. This point is not the one associated to the CN. This left point is the one associated to the identity, this point, and this point,
associated to the CN.
Yeah, this point, the blue one is associated to the CN.
That's true, yeah.
And the red thing, I could choose many red things, right? I can choose to glue in various different ways by specifying how the regions between these red points are glued across copies. Those are all valid solutions to the same boundary conditions.
Do you mean to?
Given the fact that I fixed the end points, I'm just allowing myself to glue arbitrarily in the middle. Many of them will be suppressed, they won't be important. The important one will end up being the one where there's just a domain on the left and a domain on the right, just like in the Ising model. But there is a sum over all of these locations where I could do that gluing. And that's the analog of the Ising spins. For each segment on sigma, I can choose to glue it arbitrarily.
Okay, I think this is the, okay, maybe I'll ask you later.
Okay, yeah,
sure. But just to ask that, then you should go on. Are you saying, for example, starting from the identity as you go in, you have made some gluing, say, to begin with, but you could have chosen to glue other points with each other, even for the trace row square case?
Yeah, that's right.
You have that.
That's right. Those would be suppressed.
Because the constrained solution gives you only one way.
Yeah.
But that would, in principle, have been a possibility.
Yeah. We're integrating over all of those possibilities, and the fact that we're integrating over them is mirrored here by the sum over permutations.
By the sum over permutations. Okay. Now, one more thing, if Rajesh, just 1 second, please go on. Now, one more small thing, you said phi h. There is, your wave, different components are weighted by phi h. Psi of phi h. And here phi h was supposed to be the bond dimension of that, I thought.
That's right.
Intermediate, that one link case.
That's right.
So are you summing over tensor networks with varying bond dimensions?
That's right. That's this sum.
Okay, so when you map that problem here, you have a sum over...
Yeah, so the map is each tensor network with a particular profile of phi, which is fixed by the bond dimensions, is a phi h state. But the state I'm interested in is a sum over these things, and they will, with some weights, the weights being given by the path integral. But for different phi h, there will be a different profile of bond dimensions.
I see, but in the random tensor network, what will decide the weights of the different...
It's an input. I'm telling it what phi h state is. Yeah.
Okay, that's nice.
Okay,
Rajesh, please go ahead.
No, I'll come back later. Yeah.
Okay, thank you.
I just want to say, your gluing is usually in the subsystem A, right?
The subsystem, you mean the right thing, right?
So, but then you are saying I can tune where I am gluing all that.
The gluing...
Haven't I constrained that my gluing is only...
The gluing is fixed. The calculation that I was doing is fixed at the endpoints, right? At these endpoints and at these endpoints. Okay. That's the analog of the subsystems being told what to do. Everything else is the bulk. Everything else is these tensors. Right, the boundary is being told what to do, the bulk is allowed to fill it in. Yeah.
I think that's what is coming out, but it is related or it is just you can do another
You can do it analytically. So this fact that the integral over unitaries is a sum over permutations is exactly the analytic tool that's useful, and that's being shown. That's playing all the role here. Okay.
If I might ask a small question,
Yes.
which is the number of these spins that
Yes.
you have.
Yes.
That was an arbitrary parameter.
That's right. That's right. So in the
Is it that it will get better and better as you increase that number, or
in principle it's capturing. In principle it's
that you're mapping onto the bulk.
In principle, what I'm doing is I'm writing down some tensors here, right? So there's some choice of tensors in the bulk, and if it's discrete, then by discrete jumps, I'm allowed to change what the gluing pattern is. The more finer I make it, the more I'll be able to determine where they're being glued. That may not particularly increase your accuracy though, because there are maybe other effects that we've not taken into account, which are even bigger than this. So it's not clear that will necessarily make it much better, but yeah, as long as you have a few of them, then it mirrors the calculation in the path integral, where we're really treating it to be continuous. I mean, the error is small, but yes, it gets better as you increase the number of tensors.
Okay.
It's exponentially small.
Question.
Yes.
Where does this formula come from?
This one? Yeah, this formula.
Sum of trace root bns for each of these.
Yeah, that's right. Yeah, so that's what's called this diagonal approximation. I can justify it to you later sometime, but the simple thing to say in the bulk is these are the only things which will be replica symmetric in the bulk. Right, everything where you've chosen the same phi for each term in row. That's why you have this. Yeah.
I'm very tempted to interpret these subleading terms as some sort of handle bodies.
They are handle bodies. Yeah. That's right. Okay. Good. So that's sort of what I wanted to say about these random tensor networks. Let me just tell you a little bit about this other.
Sorry,
Yes.
must go on. But if you are inputting the weight over different tensor networks by hand from the gravity calculation,
Yes.
then what exactly is the random tensor network teaching?
It's teaching you what I'm trying to emphasize from this point. So there's separate things I can say about what it's teaching you, but here what I'm trying to emphasize is the fact that the mechanism by which the random tensor network is very similar to the mechanism by which the gravitational path integral is gluing things together. I mean, in various examples. There's separate things I can say about what it has taught us, because there are situations where we don't know exactly how to do the gravitational path integral carefully, and the random tensor network calculation is much more tractable, and we can do that and then learn something about gravity. So the examples include, for example, this Renyi entropy for n less than 1, the entanglement negativity, entanglement entropy for bulk subregions, and so on. All of these are situations where we understand what to do in the random tensor network exactly, and then since the mechanism is mirrored in the gravitational path integral, we can even literally translate some of these things to the gravitational path integral. But here all I'm trying to say is qualitatively, the fact that this randomness is showing up is playing an important role in how the gravitational path integral is functioning.
So this Cayley distance or whatever you mentioned,
yes,
that by itself is not going to be a measure. That's not going to translate to a kind of the action on the other side.
It will. I didn't say that in detail, but exactly, like if you choose different regions to glue across, there will be an action cost coming from the conical defects that you set up across those regions, which will be exactly the same as the Cayley distance that you get. So the actions also match.
Okay.
Yes.
Just a quick question. These phi-s to start off with were orthonormal.
Yes.
In the semi-classical sense.
Yes.
But it can be not orthonormal if
Yes.
you take 1 over
Yes.
iteration.
Yes.
But does this sum over?
It's an approximation. This works to leading order. Okay. Yeah. So I want to.
And of course, you have to get to some punchlines. So my suggestion is that we give Pratik, let's say half an hour, only pressing questions, if that's okay for everyone. And we try to wrap up. I hope Rajesh and Gagan, we'll try to close at 12:45, but I hope you can stay till then. So thank you.
Okay, so let me turn to the second aspect of randomness that I want to mention, which is more related to the page curve calculation that was being mentioned. Okay, so in the page curve calculation, what the key tension was between the fact that the black hole can be really big, right? There can be a really big black hole with many degrees of freedom, which are, so maybe I should draw it this way. So the black hole can be really big with a tiny area. Okay, so the area over 4G is much smaller than the amount of entropy you can store in effective field theory inside the black hole. Okay, all of this stuff was entangled with the box, right? Box of radiation that we had. But the important feature was the fact that this island really only emerges when the amount of entropy beats the area, right? So that's a situation where so there's two descriptions we have. There's an effective field theory description, right? So let me call it HEFT. And then there's a fundamental description. Okay. Now there's a map going from this effective field theory description to the fundamental description. This map now is going from a big space to a small space, right? This thing has size e to the a over 4g, whereas this thing has size e to the s EFT, which can be very big. Okay. So now this is basically what's been called a non-isometric code. Okay. So it's a map from a bigger space to a smaller space. Now in the traditional discussions of ADS-CFT, the ADS-CFT is a duality. It's a duality meaning a relation between Hilbert spaces. There's a one-to-one correspondence between states in the bulk and states on the boundary. This is quite unlike that, right? This is a situation where you actually have many states in the bulk which seemingly are all different and they correspond to a lesser number of states on the boundary. This has been modeled by a random map, and in fact the West Coast model, which computed some of these replica wormhole calculations, used a model where the boundary dual, because of the randomness involved in JT gravity, is literally a random tensor network. Okay. And the map you can also exactly look at. The map is very simple. The map is roughly speaking a random map, okay, given by random coefficients going from this bigger space to this smaller space. Okay. Now this might have been something to worry about because of this non-duality. And what was argued in these non-isometric code papers, which in a language which I'll try to call complementarity star, this is basically complementarity is basically the idea of trying to have your cake and eat it too, right? So we saw that this tension was there between all of these different aspects, fundamental aspects of physics, and complementarity is an attempt to try to make that work somehow. Okay. And the way they tried to make it work was to say, for someone in the interior who has this big space, let's say they compute some inner products between states. Then what they basically said was this map V, which is a random map, preserves inner products up to order e to the minus a over 4g. As long as you access a small set of states. Okay, so for a finite observer inside, you might say, okay, they only have access to a finite number of states, and because the inner product is identical in both places, it didn't really matter which inner product we used. Okay, so the bulk observer might think they use effective field theory to compute quantities, but the fundamental thing is the real thing, that's ADS-CFT, and there's some redundancy in description in the sense that all of these different states cannot be orthogonal states because they're all mapped to a smaller set of states. Nevertheless, states which are almost orthogonal, you can find a big set of states which are almost orthogonal, so that it's almost indistinguishable to the bulk observer up to errors of this order. Yeah.
So suppose I start with the regular size black hole.
Yeah.
Then the map is 1 to 1, right?
Yeah.
Map is unique. But as the evaporation starts,
Yeah.
then the map is becoming like.
I mean, at least there's no reason for it. Yeah, here the thing you're hitting is really when the area is smaller than the size of the volume inside the black hole.
Changing up.
Because as you evolve in time, the size of the interior grows. Like there's a big space inside.
But the radiations are going to the boundaries.
But there's also radiation inside. So this SEFT that we're talking about is the entropy of the stuff that's inside the black hole. The interior stuff which is entangled with that outside stuff. That is a big space. And that entanglement is beating this A over 4G. That's why you see an island. Yes.
So I'll make sure. Let's say we had a situation in ADS CFT.
Yeah.
So you're semanticity, you got a black hole inside it.
Yeah.
And what this diagram, this balloon is actually the inside of the black hole.
Yes.
And then the fundamental Hilbert space is that of the CFT.
Yes.
And you're saying, well, it seems like many degrees of freedom inside, but mapped in this non-isometric way
Yes.
into the CFT.
Yes. Correct. Okay, good. So now, so this, you might be fine with this because this works to a good enough approximation. This is only non-perturbatively small errors. You might worry that when A goes to 0, then this is becoming subtle. But that's a situation where this black hole is really pinching off into a singularity, right? So you might say that's something we don't have to worry about, and so this rescues everything. Okay, and so people were quite bullish about this and wanted to say that we've basically resolved the information puzzle. So what I want to push back on is that very point. And in order to illustrate this, we basically had a situation where we can take, where we have a situation which is very similar in physics, where we can say all the same words and we still run into an issue. So it's really this tension with the fact that there's a bigger space on the ADS side which is being mapped to a smaller space in the CFT. Okay, and this is the situation with closed universes.
So when you say small set of states, how small?
E to the A over 4g. So it's still pretty big, but this is even bigger. I mean, it becomes small as A becomes smaller. Okay, so now in ADS CFT, there's a simple way of constructing closed universes, and this can be done in general models, where you take an asymptotic future surface and an asymptotic past surface, which would compute some sort of partition functions, and then you have a wormhole connecting them. Okay, so these orange slices are basically asymptotic boundaries. In JT gravity, for example, you could consider just circles, and then these are finite regions, and then on this middle slice, which is this dashed surface, you have a closed universe of finite size. When you evolve this into the Lorentzian picture, what you'll find is basically a Big Bang, Big Crunch cosmology. Okay? So this is a way of embedding cosmology into ADS CFT. Okay? Now, this is confusing. This is already in tension with ADS CFT. And the reason is because these boundary conditions compute something like a partition function, right? So this is like computing a partition function of a CFT. If you have a definite CFT, then of course, z of beta squared, okay? If I do the, if I represent this bar to mean doing the path integral, then this should of course be equal to z of beta squared. Okay, so whether I do the path integral before or after shouldn't matter if there was a definite CFT. But of course, this sort of contribution violates that, right? These contributions are just disconnected. They would look like the following. They would look like the following with no closed universe in the middle. Okay? So forming a closed universe here really requires the presence of something that doesn't factorize. And this is in tension with ADS CFT. In ADS CFT, we think there's a unique CFT, and this CFT cannot, and is in a CFT, a partition function is just a number. If it's a number, then it should square to the same thing whether you do that before or after the averaging. So when I look at the big, like the Lorentzian picture, so this is the Euclidean picture I'm drawing. The Lorentzian picture will look like the following. It will be like a circle of some finite size, which evolves in time and forms a Big Bang, Big Crunch, like Big Bang, Big Crunch. So it has a singularity in both the past and future. It's an ADS cosmology, basically. Very good. So now we can try to, so this is what's called the factorization puzzle. Okay, and this factorization puzzle is a puzzle when we think about standard ADS CFT. Standard ADS CFT has this lore that there's a unique CFT that's describing the bulk. Whereas in JT gravity, the randomness is very important because that randomness allows you to have this non-factorization. Okay, when you have a random average, the average over z squared need not be equal to the average over z whole squared, right? This is basically, there's some variance in the partition function itself. So in JT gravity, this is not a puzzle. This is in fact a perfectly reasonable way to construct closed universes and try to describe them. But it's super important to have randomness or some other variables describing these CFTs. There's some class of CFTs that you're averaging over in order to obtain something of that sort. Okay, so that's really the puzzle. And in 2 dimensions in this JT gravity, this is not a puzzle. Okay. Now, you can ask, what do I need in order to make this work? Right? So either you could just by hand get rid of these things, okay, but then you would get rid of all the things we got, which led us to the calculation of the page curve. The important feature in that led to this computation of the page curve was the presence of these wormholes connecting different boundaries. Right? It was important that we were able to swap universes and so on. Okay. So we would get rid of that if we completely got rid of these wormholes. On the other hand, you could also say maybe there's some additional contributions to this which somehow cancel it out, and that still doesn't solve the problem. And the way to see the problem is as follows. So you can construct situations which look like this. Okay. So now we'll just use something of this sort where you have the geometry looks as follows. So we'll construct this in ADS3 for concreteness, but there's nothing really special about it. So this is like computing the torus partition function at large beta. So there's some beta over 4, okay. And there's some heavy operator insertion on these circles, which I'm going to identify with each other. Okay. So it's just some O, which is a heavy operator, O dagger. And the bulk dual of this heavy operator is essentially a shell of dust. Okay, so the shell of dust looks as follows. It follows some path in the bulk, and it's glued to each other, right? So the geometry in the middle looks as follows. So on one end we have ADS, on the other hand we have ADS, and in the middle we have some sort of spherical geometry with a shell of matter in the middle. Okay, so you start from one end, the radius goes outward, you go to a big circle, you hit the matter, then things start crunching again, and it becomes a closed cosmology, spherical, and then this evolves in time. Okay. When this evolves in time, again it forms a Big Bang, Big Crunch cosmology that's supported by this matter. Okay. There's many ways of constructing such solutions. This is one example. Okay. In particular, what we're doing is basically taking any of these solutions which have these closed universes and drawing tubes through it such that the dominant solution continues to stay that particular solution. Okay. So this is a situation where we're going to take beta large. Okay. So famously in ADS3, there's 2 phases for the torus partition function. There's the thermal ADS phase and the black hole phase. And so we're going to take beta large so that we're trying to be in the thermal ADS phase. Okay. So these surfaces just look like additional ADS regions, which have some entanglement with this closed cosmology. Okay. Okay. So these things can be constructed.
So the outside tubes are behaving like an ADS.
Yeah, the outside things are ADS. These things.
No, on that there was a figure.
Yeah, the outside things are behaving like thermal ADS. That's right.
The region inside the tube.
Yeah.
Is the closed tube.
The region.
Yellow tubes.
Yeah, exactly. So this is one inside and this is the other inside. Okay. So now we can do various things with this and see. So this is in higher dimensions now. Okay. So in higher dimensions, the expectation is that ADS CFT has a unique duality. There's a one-to-one correspondence. There's a unique CFT and so on. Now you can phrase various puzzles. Also note the resemblance to the page curve calculation. The resemblance is that this closed universe is now in the island of this left union right CFT. Okay, so if I want to look at the left and right CFT, just the ADS regions actually have a mixed state. Okay, each of these has a mixed state, but it's purified by the closed universe. This closed universe is playing the role of the black hole interior. Okay, now in order to include the closed universe, I can include the entire closed universe without any area cost. A closed universe doesn't have a boundary, and so it doesn't incur any area cost. And on the other hand, it's benefiting you because it's decreased the entanglement. Since it's decreased the entanglement, its advantage is always to include the island. Okay, so this is very much like the post-page time black hole. But now it's in a limit where the only thing that's costing you, the thing that plays the role of area, is the entanglement between these universes. Okay, so if you try to follow the same logic that was followed for these non-isometric codes for the black hole situation, you find that there's a map which goes from the closed universe, or let's just call it the EFT, to the fundamental description, which is supposed to be the CFT. And now this is huge. Okay, huge meaning this universe can be arbitrarily big, right? We can make this universe arbitrarily big, independent of what we're doing, and the amount of entanglement is tiny. Okay, it can be order 1. It need not be scaling with 1 over g at all. There's no area cost, and so it's just an entanglement cost, which can be parametrically small. You can even take it to 0. Because of high beta. So if I take beta to really infinity, it will become 0 literally. So it'll just be one state.
So H fundamental is factored into H left into HR.
H fundamental is H left times HR. Yeah, that's right.
Doesn't the nature of solution relate to the thinness of the tube to the thinness of that the yellow tube?
The yellow tube size is dictated by the mass of this operator insertion. So the bigger it gets, the bigger this universe gets.
It can go bigger than that tube.
Yeah, it can be much bigger than the tube. Yeah.
So I didn't answer that if you set beta to 0, even at 0 temperature,
Yeah.
I can have entanglement entropy.
You can't, you said?
Ground states have entanglement.
No, in the thermofield.
In the thermofield level. Like in this particular example, this state has
that was my whole question starting, that thermofield doubles are usually very bad descriptions of ground state.
That's correct. So in this,
why are we taking that towards the ground state?
in this, let's say we're in ADS 3, then the spectrum looks like this. There's a unique ground state, there's a gap, there's a few states, and then there's some continuous spectrum above some value. That's the black hole phase. But we're not in that phase. We're at large beta. So we're focusing on these tiny number of states. It's a very sparse set of states. And in fact, if you take beta to infinity, you'll basically focus on the unique ground state. There's a unique ground state. So we're focusing on that, and the entanglement then has to be tiny because it cannot be big. There's just few states. The number of states here is just some order 1. Here, it's e to the 1 over g. It's a sparse spectrum below the black hole threshold. In gravity, basically the only thing that causes like this dense set of states is black holes. And you're not in the black hole phase. You're just in a regular empty ADS phase with some matter floating around. The amount of matter is just order 1.
So you're saying the corresponding condensed matter would be having a large gap phase.
Yeah, exactly. Exactly.
The area long.
Exactly. Yeah. So it's not like a spin glass or something. Yeah.
The number of single
Or a
trace,
Fermi liquid or a
Yeah,
Fermi
yeah,
seed will
yeah.
not be there.
No.
You have no state.
the number of single trace operators is order 1, but of course you could have a gas of them.
Yeah.
As long as you have less than n square, you can still have a large number.
Yeah. All I want to say about it is order 1, and we can also tune beta independently of this mass so that we can make it arbitrarily small. Like we could really make it 0, right? It's just going to zoom in exactly to the ground state.
Okay, but I'm just saying to come closer to the black hole situation.
That's right. So
you want more stuff, but not so much that you form a black hole.
Exactly. So we
So
can
you
tune this
have
parameter.
into this
Exactly.
1/5 or something,
Exactly.
1.5 or something.
Exactly. So you can tune this parameter so that it resembles more and more the black hole, but you can also tune this parameter to look more and more like this factorization puzzle, which was where we didn't have anything really. So it's really playing a role of interpolating between these two things.
Sorry, but since we are not in a black hole place, why are we talking about this map?
Because there's still a map. I mean, there's still this closed universe which is encoded in the boundary.
In the black hole.
There's always a map. There's always the ADS CFT is always a map from bulk to boundary.
But there
right?
was a unique map, and now.
Yeah, and now what I'm saying is even in a situation without black holes, this is something where there's a non-isometric map. Even in a situation without black holes, the closed universe is playing that role. Okay, very good.
It seems a little more tractable because it's shown of the mysteries of horizons and
Yes,
so
yes.
on, but replaced with the closed.
Exactly. It's in the closed universe is in a regime where it's like semi-classical in the regular sense. It's an arbitrarily big universe. We could be living in it and so on. And nevertheless, the map to the boundary is tiny. Okay. So now you have two options. You can say that the bulk inner product, the inner product that's relevant for an observer in the closed universe, as it would be for the observer in the interior of the black hole, is determined by HEFT. Okay. if this is the relevant inner product, then that's basically saying that ADS not equal to CFT, right? Because that's saying that the description in the interior is not captured by the CFT. There's a big non-trivial Hilbert space of states that's in the closed universe. Somehow when we map it to the boundary, we lose all of that information, and somehow the CFT just doesn't know what the experience of this observer inside is. Okay, that would be, so that's where the tension is coming from. If on the other hand, like the story with this complementarity, you would try to say that this is the relevant inner product, then so then what you end up with is essentially no semi-classical closed universe, right? Because what you find is that the effective field theory has large corrections, right? We saw that the corrections to the effective field theory, so we saw previously that the inner products in the effective field theory and the fundamental differ by amounts of order e to the minus a over 4g. But we've now taken a to be tiny, right? Since we've taken a to be tiny, there's the things that effective field theory computes are just completely off, right? And that would basically mean that there's no semi-classical closed universe, okay? In the strict limit where we take beta to infinity, it's really all of the closed universe is mapping to one state, okay? So this is the statement that people have been using as a slogan, that the closed universe has a one-dimensional Hilbert space and so on, okay? So this is basically an avatar of that, but it's also continuously connecting it to the black hole. Now, in this particular situation, you would, the picture you would have in mind is that when we have these solutions which involve asymptotic boundaries being connected by these wormholes, then there are additional things that you need to add in order to make it work as follows. You would, yes.
What is the direct issue with saying that the closed universe has very few states?
It's in conflict with effective field theory. In effective field theory, we have a gigantic number of states. Like, I mean, you know, in this room, we have more states than 2.
Can you use the gravitational path integral to explore this big phase space?
Yeah, you can. Essentially, what you can do is add particles around this, for example, and those would be excitations inside the closed universe. So you can have GeoD6 going in these regions, and so those would be like excitations, and you could access all of that. And what ends up happening here is that all of those states actually get mapped to almost parallel CFT states.
They are different super selection sector in some sense. I mean,
okay, that's another option which I'm getting to. That would be something else, which is possible.
because in DCP also people sometimes say only one state or whatever, right?
Yeah. I don't know.
As a universe, there might be, we are just in one state, right?
Yeah, so it could be you say that.
We are having multiple states.
We would then have to explain how, I mean, regular quantum mechanics, we always assume that we have the non-trivial Hilbert space and we're dealing with that. We would then have to embed all of that in one-dimensional Hilbert, whatever that means, in numbers. So that would require some new thing. But certainly it wouldn't be semi-classical closed universe in the standard sense. In the standard sense, meaning just the effective field theory closed universe.
No, even effective field theory, you have to do something outside it to make it to explore that phase space.
No, that's within effective field theory.
No, but these operator insertions were to,
That's just a map. So I can consider this effective field theory and then just look at some excitations here. Those can be mapped to the boundary. They'll be related to something that's coming from an operator insertion there. So they can be mapped to the CFT.
This super selection sector, which I guess you will.
Yeah, we'll talk about that.
And you're running out of time, but I thought you were going to say something like this, that, okay, you start, as Shiraz was saying, you start exploring this phase space
Yes.
of inside the closed universe by various operator insertions and so on. And it works fine for quite a while, but if you put too much stuff, then you start forming black holes.
No, this happens way before that. So because this is order 1.
Works, but what I'm saying is that, the non-isometric nature of your code really reveals, is fine for a while if you have a small enough Hilbert space being mapped to a big one. Until the Hilbert space you're trying to map itself gets to be of order, e to the n squared.
No. It happens much before that. Because there's only an order 1 size Hilbert space on the boundary. So here I may have an arbitrarily large Hilbert space, all order 1. Let's just say we are in, we never access black holes at all. We can just have a gigantic universe with big volume, which has 10,000 qubits worth of stuff, and on the boundary we're mapping it to 2 qubits. You hit the problem at 2 qubits. That's way inside effective field theory. We never access black holes.
And that 2 can be held fixed,
Yeah.
even independent of what operators you
Yeah.
insert it.
Yeah.
So it looks like a sharpest.
Yeah.
Right?
Yeah.
You mean you order one
I mean, we hold fixed this beta so that you're always mapping to the same Hilbert space, and then we can act with all these operators. All these operators are basically, there's some non-trivial heavy operators. They're all getting compressed into this two-dimensional Hilbert space. There's not that much room, but you can still access this whole gravitational phase space, this number of effective field theory states, while staying within this 2.
Yeah, he's constructed a huge phase space, but which should be encoded in a much smaller space.
Yeah.
The CFT Hilbert space at low energies.
Okay, good. So so relating this to the factorization puzzle, as we said before, if we believe that ADS CFT in higher dimensions is just a unique duality, there's just a single CFT that's corresponding to all of this, then something must break factorization. So there must be some other effects, right, of this sort. Where they add to this contribution and somehow cancel the contribution. There have been some toy calculations of this. They've been called half wormholes. These are ingredients in the gravitational path integral that we are far from understanding. But nevertheless, this would be something like a firewall, right? Essentially, in this situation, the analog of a firewall is the non-existence of a closed universe. Right? And these things would basically spoil the closed universe. They're basically damaging the closed universe. So this, if we could find what these ingredients are, that could hint at the presence of some extra ingredients that we're missing in the effective field theory, which seem to be relevant in these scenarios. And nevertheless, and then if that's the case, that would also have an implication for the black hole interior, because in the black hole interior, we've been wondering, what are these firewalls? Like, if that's the way out, what is the dynamics of these things? This would be a way of trying to get at that.
Sorry, but Pratik, this is now to be interpreted in a Lorentzian way, right? So I don't see why the existence of this, undermines the puzzle that you have raised here.
I mean, it would basically say that you had this good solution, and you can ask what spoiled it. The thing that spoiled it was that there were all of these other contributions which were very comparable. So yeah, they're also competing with that somehow. So when you try to describe in EFT this thing, you have to keep track that there were also those other effects which could spoil your description.
Universe state and also kind of nothing.
Some nothing state which involves some amplitude with these erratic. I mean, that's just a toy picture, so I don't know what it is, but yeah.
Just to ask you,
Yeah.
you do know enough to be able to construct the map, right, onto the CFT.
Exactly. We can write down these states.
And so you know it's a highly compressed map.
Yep.
And you know all the details
Yep.
of it, right?
Yep.
So the states which are looking orthogonal in the closed universe because they are exploring the full phase space.
Yep.
Are it's a radical breakdown of effective field.
Yes, that's
I
right.
mean, isn't it like basically taking all these states near the heavy operator and passing them through e to the minus beta?
That's exactly right. So you start in the black hole Hilbert space in some sense. It's a dense set of
So you know
states,
what is happening.
and then pass it to the. I can write down what this state is, right? So it's not even a yeah.
Sorry, I missed the point. In this particular example, I understood why there is a huge CFT Hilbert space.
Yeah.
But why there is a tiny?
Because the number of states here is really small. So because we've gone into a regime where there's order 1 energy and order 1 entropy. There's only the only states in this region are like vacuum ADS plus some tiny excitations. No black hole Hilbert space. Okay. And the other way out of this is related to the fact that randomness can be important. So remember that in JT gravity this was not an issue. The reason it wasn't an issue was because there were these things we were averaging over, and it has been shown by Marolf and Maxfield that there's actually a one-to-one correspondence between having these non-factorizing contributions, so the Hilbert space of effective of closed universe that is constructed in this particular way, and the number of things that you're averaging over in the boundary. Okay, there's some correspondence between these two things. So
also
yes.
you're in a regime where the field theory Hilbert space has a good large element, right?
In some sense, the state that we take, it doesn't have a good large N limit, because the state has come from the OP coefficient. I mean, it carries the OP coefficients of these heavy operators, and so when you push it down, there's some erratic coefficients which are related to n. So it's accessing the dimension, and everything is held fixed as n goes to infinity, but the state is not. So that there's some subtlety in that. Good. And okay, so this was a paper we wrote 2024. A lot of people have made different proposals for how to get around it. So just to complete what I was saying before, in the Marolf-Max field picture, we have something to average over, and then you would have a non-trivial description of the closed universe using these extra parameters. The extra parameters being the stuff that you average over. Okay, but that would also be unfamiliar because that wouldn't be like ADS-CFT. In higher dimensions, we expect there's nothing to average over. Oh, ye khatam ho gaya.
When did it get
Abhi hua?
Just now only? Okay. Just come
Okay.
back on.
Just wait there.
I'm taking advantage of the pause.
Almost done.
I mean, I thought that's what you would say, that you have these random coefficients, and if you're allowed to average over them, then you have the closed universe.
That's right.
If you're not, it's not so.
That's right. That's right.
Okay.
I'll just wait for them, I guess. Sorry, you're fine with it? We could be in it. Yeah.
Even at a large base.
It's like, it should be thought of as a difference in oscillations.
But it's all within the same field theory.
Same field theory, but as a closed universe person, I cannot do anything with that. I cannot make that, right?
Yeah.
If I'm in a closed universe, I cannot make that particle.
Yeah, so that's also a reasonable way. So super selection sectors is like this Marolf-Max field type thing, in which case you would have.
You do it something outside to do that.
Yeah,
Like
and
as a closed universe person, I cannot change myself.
Yeah,
But
yeah.
I'm destined to crunch.
Recording in progress.
How about dissonance? That's also closed.
Yeah.
I mean in any
My
closed
classic
universe, I guess.
States I can create for you. I can reconstruct them.
But that's very asymptotic, right? Because you have some.
I can count states.
My video is off. We can hear the discussion.
Oh, you can hear the discussion?
Yeah, in between it got disconnected, so that's
Yeah,
why.
sorry, yeah, I'm just waiting for that.
But I think we'll just let Pratik go on and then.
I'm close to done anyway. So all I was saying was, so there's these few options that we have. It's a sharp tension in ADS-CFT in trying to explain this thing. And one of the ways out is, of course, randomness, right? So in this situation, this Marolf-Max field Hilbert space suggests that we can have all of these different superselection sectors, as Abhijit was pointing out. But as long as in this translation, we're talking about these different CFTs that we're averaging over, which we don't quite understand. So either we have to change ADS-CFT in the traditional sense, or this is suggesting something very drastic about the bulk, and in particular about both cosmology and the black hole interior. Okay. But in this case, one interesting thing is that you don't, one thing broadly speaking that has been proposed in the last year or so is any kind of averaging, any kind of randomness will solve this problem, right? So this non-semiclassicality of the closed universe, like basically these erratic fluctuations that we're talking about, essentially get washed out when you do any kind of averaging. And so you can do averaging over these different alpha parameters, which is like this Marolf-Max field type structure, or you could average over other things, like for example the operator that I use to form the closed universe, or even.
Sorry to interrupt,
Yes.
you're way out of time, so for later, but see, what I thought was you do need to insert some kind of a heavy operator.
That's right.
Right? So now that means it's not all that simple.
That's right.
You know, maybe it maps in a single CFT to an operator with suitably random coefficients.
Yes.
And that averaging, if you're willing to do, you
Yes.
have the closed universe.
That's right. So if you do the averaging over that, that's right.
It doesn't require you to sum over CFTs and abandon.
Correct. So as you said, like there's any kind of averaging will help that, but there's many other ways in which, I mean, there's many wormhole solutions we have at this point. Many of them don't involve these heavy operators and so on. So in all of these situations, there's some control you have on these things, and it seems plausible to just construct that state and ask about this thing.
Like very briefly, just
Yes.
I haven't understood how averaging solves anything. Because you've got a huge phase space in the bulk.
Yeah.
It's all mapping to, let's say, one state of the boundary. What does the averaging bind?
The averaging, I mean, because the averaging is buying you that you're not always mapping, I mean.
Let's say I'm mapped just to the vacuum state and beta's got infinity.
No, but you're averaging over, I mean, let's say you have many CFTs, then you would be mapping to the...
Not CFT, I'm allowed just randomness.
So then what you would say is that the bulk person measures the fundamental inner product after averaging.
But I'm not worried about in terms of inner product. I'm just saying that if I have a huge phase space in the bulk, it should not all map to the same state. And I don't see how averaging helps you.
No, but then you're not using it that way. I mean, if you think it's not resolving that issue.
It's not
resolving that issue.
It's still a paradox.
Okay, that's fair. I mean, so what has been proposed is for the bulk observer. You could imagine that the bulk observer, there's some rule that tells you that the bulk observer never knows enough about the closed universe to utmost precision to measure things precisely. And that's why it can never actually measure the fundamental inner product, in which case some averaging will save you. But if they were precise enough to do whatever measurement you like, then it doesn't save you.
But you're saying, averaging or not, it's just true according to this proposal, that a huge phase space in the bulk
maps to a single state. But that we should always, I mean, even in the page curve case, we should have been worried about that. There was a huge phase space which was mapping to a much smaller phase space. That was already true there.
We should talk about it more, but whether there is a bulk or not, whether there is a closed universe or not, may depend on whether you average or not. That's all it is. If you don't average, you keep everything, then you may not have the closed universe.
That is exactly, so that this is one of the kinds of proposals that people have tried to make. It's true that any kind of averaging ends up with that. So this is something I like to call ignorance is bliss. Like any kind of ignorance existing will give you some semi-classical description of this closed universe. But it's not clear if the bulk observer is limited in any way to have this ignorance. Like what if they measured everything? Do they just die? So I think this is still something that we need to understand.
I think it would be most satisfying if from the bulk point of view we could see that there were wild fluctuations.
Yeah, somehow that's this kind of picture where we're saying that there's definitely like some other ingredient which we don't understand, which is spoiling effective field theory. But that would then be very close to the firewall type scenario where it's saying that the interior of the black hole will also have these wild fluctuations for some reason. So that is what would have to happen, and that's also an interesting possibility. I'm agnostic to it, but people have been thinking about what these options are.
That solution there, is that a dominant solution?
Yes. You can make it the dominant solution. Basically, any time you can have these cylinders being a dominant solution there and these can be constructed, then you can construct this kind of thing. I mean, there was some controversy around this because you need to assume something, but there are other situations where you can make it happen. So.
I think let's close that.
Yeah, so I was basically done, so thanks. Yeah.
Okay. All right. Thank you very much. Okay, we had a lively discussion, but if there are a few questions, or in any case, we are happy to take questions. Maybe we'll take first from Gagan and Kapil, and Rajesh, excuse me. Go ahead, please.
Yeah. Can you hear me?
Yeah.
Right. So I don't have an exact question on the sort of the thing that you sort of discuss is more, let's say, for the experts. But one point I wanted to sort of check with you is a more like a broader perspective. This ADS CFT, the technique, the framework or whatever has been developed in the quantum gravity string theories. So I just know, that it is used in this story of warp group plasma, more like story of this strong interacting system. So I was wondering, like, imagining you are at TIFR and there is theory community, strong interaction people across your room, and also there are experimental groups working on Alice and Star and all experiment. So I just wanted your perspective on how you foresee sort of talking to colleagues across the corridor on these strong interacting systems.
Oh, I see. I mean, there's certainly been a lot of effort in trying to use ADS-CFT, I mean, back in the day, or in order to understand things like the field of ADS-QCD and so on. There's definitely a lot of things where it's useful to, you know, I mean, there's a lot of commonality with people working on, say, QG, like Rake and so on. Moreover, one of the things that has emerged recently, this is one of the things that I find very interesting, is the presence of this random matrix theory. You know, random matrix theory has shown up a lot. It showed up in, you know, these random tensor calculations that I did, and this JT gravity and so on. And of course, random matrices initially were, you know, designed to talk about nuclear physics, right? So it was any sort of complicated system where we're trying to simplify that description has this feature. So it seems like something, some commonality between these fields, and that seems like something which would be nice to understand from both directions.
I think the question was, can you imagine yourself increasing?
I mean, because of this fact, I mean, the fact that I've been working on these random tensors and random matrices and so on, I would certainly be, you know, interested in understanding those aspects of, you know, treating these complicated systems in some way. That's what I meant. Yeah.
Okay, thank you. And one small question, it was a remnant from your last talk.
Yeah.
It's a very basic question, and maybe it is too naive. When you did this, that SBH, and you essentially wrote down that equation, the Boltzmann constant, C squared, ABH, area of the black hole upon the 4 square root of, H bar G, capital G, right?
Yeah.
And then you essentially set all these KBC, H bar, I mean, what we do in particle physics, the natural unit. So you set them to be 1, right?
Yeah.
So the question I was asking, you know, that if you're working on the quantum gravity realm, I thought you can also set up the capital G to be 1, right?
Oh.
10 to the power of the Planck scale or Planck. So
good.
I was kind of, I mean, I thought maybe it's too naive question to ask.
No, this
so
is
it's just the SBH being proportional to ABH should have been done with that. Right?
Very good. So sometimes we even say A over 4. I mean, that's right. We can also set G to 1. Sometimes it's useful to keep that scale. So if the only scale in the problem was the Planck scale, then that would be the case. But sometimes in ADS CFT, for example, there's a separate scale, which is the ADS scale. Right? So there's a, or in our universe would be the Hubble scale. So sometimes you set that to 1 and then try to describe things in terms of that. So it's not, sometimes you just keep G to keep track of that.
So we're not always dealing with that Planck scale.
Yeah.
So, you know, you want to keep that so that you can do the connection.
Yeah, you could treat that as 1, and then the ADS scale would show up in various places, and I mean, yeah, it's a convention.
Got it, thank you. Sandeep, I'm done.
Oh, okay, thank you. Rajesh, anything from your side?
Maybe a very general question. So, do you envisage the random tensor networks being able to? I know they are very built to capture the entanglement structure, but do you think they can capture other observables in a conventional ADS CFT in some sort of even in qualitatively some features? Do you think they can capture?
Yeah, this is a good question. I mean, because of this randomness, you're sort of washing out some of the details. So if you know you're computing something that's very sensitive to the particular theory, then you sort of lose that. In the original random tensor network paper itself, they talked about correlation functions and how you could find correlation functions using this random tensor network, again averaging over tensors. But it's unclear. Like for example, as I was saying, the Mera tensor network constructs the ground state. So let's say we were interested in some higher dimensional CFT, then it would you can explicitly construct the ground state using some Mera ansatz, but there the tensors would be some particular numbers, right? And it's going to be important to have those precise numbers to get all the correlation functions right. So it's unclear if this complete averaging over this large Hilbert space and so on will capture things. As Rajdeep was saying, when in condensed matter you try to do this, you end up with something which is very high temperature generically and so on. So it might miss those details, which is why I think it hasn't been used so much in order to explore standard things like say correlation functions so far. It's mostly been used to explore entanglement structures. It's been useful for the entropy, negativity and other things like that.
Sure. But I was thinking, pushing that a little more about the fact that it's strong coupling, there's a kind of a universality in that Einstein's gravity captures correlators, captures many things. So that part of that universality that is there, So do you think
Yeah.
at least the Einstein gravity piece, which is, as people say, I mean, it's geometrizing the entanglement, that part of it at least do you think there's potential to capture?
Okay, I see.
I mean, it's a little big.
No, I see what you mean. At this point, like, you know, as we saw, like, there's a lot of input I took from the gravitational path integral as well. It's hard to imagine that the random tensor network would, I mean, maybe there's some way, but there could be some way to see that. But another thing that the tensor network doesn't see so far is dynamics. And it's been hard to understand time evolution and so on in this language. There have been I mean, it's also true that, you know, because we're dealing with chaotic Hamiltonian, sometimes you model the time evolution itself as a random unitary, and that also works for some purposes. In fact, like some black hole calculations almost match precisely with the thing you would compute by doing this random unitary evolution. So for some purposes, it works. Like for example, for the calculation of an out of time order correlator. So maybe some souped up version of this random tensor network which includes time evolution could know a little bit more about it. But otherwise it's a little hard to imagine, because, you know, these tensor networks could, it's not clear where they know about the coupling and you know, they know about n in some sense, because this large bond dimension limit is being taken, so n is being taken to infinity, but it's not clear whether they know about coupling. So that's the thing I'm a little suspicious about. One thing I should say about this is I have some hope for how to go beyond this by looking at this model which is called double scaled SYK. This double scaled SYK is a model which has a controlled double scale, like triple scaling limit to JT gravity, but it's some discrete version away from it. And the bulk picture looks very much like a tensor network. In fact, the limit, the opposite limit from the JT gravity limit is precisely a Gaussian random matrix. So there's some connection there which I think might, you know, we may be able to interpolate between tensor networks and standard gravity by using a model of that sort.
Okay, good.
Yes. Anything else, or are you done?
I'm done. Thanks.
Okay.
Amol.
Yeah. Amol, another question. So of course there are many approaches people have taken to look at this information problem.
Yeah.
Right? So yours is one of them.
Yeah.
I don't know about many of them, but for example, one that I have heard recently of somebody getting about is this approach taken by Surat, for example.
Yes.
So what is the difference? Can you?
Yeah. No. I mean, I think like
the difference in the approaches, and maybe if there is any difference in the predictions.
Yeah, I think there is, we agree on almost everything except this one qualitative point. So let me just explain what the point is. The point is basically if you have a black hole in the middle and let's say it's radiating out, so all of the radiation has been collected somewhere near the boundary, okay? Then actually maybe one way to say this is there's you can try to compute the entropy of all this stuff. Okay, so there's something I didn't get a chance to say about these holograms. You can try to compute, say, the entropy of some region here. Okay, so let's say all the radiation has been collected outside at some point, and you have access to the entire algebra of observables there. Then what Suvrat's claim is basically once you do that, then you have access to the full bulk. Okay, so in this case, if you try to compute the entropy using the island rule, or this Ryu-Takenagi formula, you'll basically include an island which includes this entire region. So for him, if you were measuring that algebra, then entropy as a function of time is just this. It's just always 0. And the reason is, you can think about it from the perspective of the CFT. In ADS CFT, the CFT is supposed to know everything about the bulk. So even when you were forming this state, it knew everything. At later times when the black hole was there, it still knew everything. And afterwards when it's evaporated, it still knew everything. So at all times it always knew everything and it was evolving unitarily. So that's a way to get this answer, which is just 0. Okay, so that's not the page curve. And this is what Suvrat was pointing out, and this is correct. Now the counterpoint to that is you don't need to do this experiment, you can do a different experiment. So you can imagine a situation where, you know, let's say the black hole radiated out to some sphere, we collect the radiation there, and then, you know, I carry it in boxes and then eventually put all the radiation here. Okay, so all the radiation that's entangled with the bulk is kept in one corner. You can engineer situations where this happens in ADS-CFT, and then measure something else. You can measure the entropy of some region which is just close to this. So let's say some region like that. Okay, if you measure the entropy of that plot will actually look more like this. And the reason is for the same reason that the island formula holds. Initially the entropy will grow, and then eventually it will fall because of islands. This is something that's very tied to the radiation. So here importantly note that we've ignored some part of the boundary, right? So what we're trying to do is somehow isolate just the radiation. If you keep track of too much, then you don't have a page curve. You just always know everything. But if you somehow try to isolate this radiation, and that needs to be made precise, in certain situations it can be made precise, but there's still some argument over that point, then you'll certainly see a page curve, and they agree with this, and they call this, seeing a page curve with blinders on. So it's like if you forget some things, then you'll see a page curve. That's the difference in approaches.
And then because at t equal to 0 and at very large t, that ignoring the part will ignore doesn't exist.
Yeah, exactly. Because now you have access to everything, so they'll match on those sides. Exactly.
This isolating is it like making transparent boundary conditions there and putting it outside into another field theory?
This isolating, one of those things is like the thing you call plasma ball, or like that sort of thing, like where the black hole is localized in some region and the stuff you have is elsewhere. Sorry? No, that's a different thing. That's a different thing. No, there are solutions. There are solutions where basically the black hole is sitting in some corner, roughly speaking, and the radiation is everywhere else. So you can isolate the region of the black hole from everything else.
Yeah. But there was a page curve even in field theory.
Here I'm talking about the page curve in the field theory, like some region of the field theory, some region of the field theory. So that's a precise algebra. So that would see a page curve, and I think he would agree with that.
There's also the state dependence of
state dependence is that's actually a very important part of this complementarity star that I was saying. It's basically a souped up version of state dependence. Like state dependence plays a very important role. So that we of course completely agree on. But as he himself points out, you shouldn't agree with it so fast, right? Like there are problems with it as well. For example, finding the Born rule violations and so on. This new paradox, I think, has similar issues for the same reason. The kind of things that he was pointing out. Yes.
Yeah, please.
Sorry, the farthest from this topic. I'm a theoretical computer scientist by background. Been reading some of these sort of questions, trying to resolve this puzzle, because there have been several attempts in recent years of using complexity theory and quantum complexity.
Yes.
In fact, you mentioned it as one of the tools that are used in your talk. Right? And in several of these, I've been attempted reading these papers in the last couple of years. One topic that keeps frequently appearing is the notion of pseudo-randomness.
Yes.
This is a notion that is in complexity theory, which is extremely well studied.
Yes.
But to understand pseudo-randomness, we need to know what is random,
yes,
whose eyes it is random,
yes,
randomness. And already in today's discussion we had, there was a lot of questions. So I don't know how you use these hammers of quantum complexity and pseudo-randomness in this in your work out here, or how does it fit in this?
That's a fantastic question. So for most of what I was doing, I was really using randomness, and you can replace some of those things with pseudo-randomness. That makes the calculations, of course, harder sometimes. Like for example, the thing I was trying to,
Once you come to that, we need to talk about randomness in whose eyes. Because randomness is like beauty, it's like in the eyes of the beholder. So we need to make that very precise before you go on to talk about pseudo-randomness and stuff. And this is been my shaky part when trying to understand these papers. I never managed to get this part in. So I was wondering if...
So when people talk about the randomness or pseudo-randomness in this context, it's in this map. So this map is a pseudo-random map. So essentially the complexity comes in trying to decode. So you have some access to some system which is this fundamental description, and you want to decode what's happening in the effective field theory description. That is a complex task if the map is pseudo-random or random. So that's where it's treated as random.
Complex for whom again?
For the boundary observer who's trying to decode what's happening inside the black hole. So someone who...
So these are places where I got to sort of need talk complex is usually in terms of a resource.
Yes.
So what is the resource in which, for which it is a hard problem or a complex problem for the boundary observer?
Good. So imagine that this observer is collecting all this.
Number of unitaries, or is it?
It's a number of unitaries. So if you imagine that you're collecting all of this radiation, that radiation is some number of qubits, right? This task of decoding what's happening in the interior at some intermediate time is exponential in the number of qubits that you've received. So in that sense, it's exponential in the sense that the number of unitaries you'd have to do. So there's a very specific task, for example, to decode a particular bit in the interior, right? So you want to figure out the state of a particular qubit in the interior of the black hole, given the access to the radiation. Now, in principle, this is doable, but in practice, it's really hard because of this high complexity. And what that means is you have to implement some very exponentially long unitary circuit in order to implement it. Okay.
Just, I know very little despite but then you should go on. But is it supposed to be a pseudo-unitary, pseudo-random? I thought the Hawking radiation is supposed to be pseudo-random.
That's correct.
Because it has that information.
That's correct. The black hole S matrix is in some sense pseudo-random. The process, so we often model black hole evaporation as you're acting with random unitaries and then bits are escaping from it. But really the dynamics in gravity is fixed, right? I mean, at least if you're assuming something like standard ADS-CFT, there's a fixed Hamiltonian, and so that will implement some fixed unitary, which is pseudo-random in the sense it kind of looks random if you have access to a small enough system. But it satisfies all the properties. It's indistinguishable from random.
So there's this notion of it's going to take exponential amount of time.
Yeah.
Exponential in what? So there is some underlying representation and things. There's a certain number of qubits to actually represent the object.
Yeah.
Underlying whatever you're studying, and then the task takes exponential time in this.
Correct.
No, but it's all a matter of representation. For example, let's go to representation. Factorization is an easy problem. If you write it in the binary representation, factorization is a hard problem.
Okay, got it.
Representations when we talk about math and physics. But here, once you bring in complexity, we need to talk about what model does are these coded, how are these stuff? All of that becomes very vital, and I don't find a reference to.
Yeah, so I mean, much of this is explained in this classic paper of Harlow and Hayden, which talked about this. And the idea is when you're receiving all these qubits, the natural representation is the representation of those photons. Like let's say these are photons, then there's some product basis of those photons. That's the natural basis that we take as the reference state, and then you want to achieve some state, which is this complex state. That process requires an exponentially long unitary in terms of that. So the product basis is really important because it's something that you don't really know about these complicated dynamics. So it's important to take that representation. Otherwise, you could have just solved the problem at hand and said it's easy, as you were saying in the unary case. Yeah.
Okay. Anything else, Amol or Basu, Rajdeep? Last word must go to Shiraz.
I just wanted to follow up on Amol's question.
Okay.
Suppose we have an asymptotically flat space and you insist on that, and then you want to compare with Subrat, then what would you say?
Yeah, I think you would have to then define some algebra on, say, a cut of scry where you're collecting part of the radiation. And I mean, the thing that really screws you over here is basically having the ADM Hamiltonian. So you would have to define some algebra. I don't know if this has been done precisely enough to be happy about it, but
so it's just
you'd
the
have to
of the news operators.
Yeah,
which
within
like
some region.
consistent.
As far as I can tell, but
Seems
yeah, I mean, yes. I haven't studied this very carefully, but as far as I can tell, I would think that's a well-defined algebra. Suvrat, of course, has complained that
he complains that it's unnatural, but
it's unnatural.
It's ill-defined.
Okay. Maybe it's a function of time. At this point, I don't know what he thinks, so you should ask him.
So this is the algebra of all generators alongside.
Yeah.
All news operators, all the radiation. I just drop this area, man.
Yeah.
Just drop it, and then you can.
Yeah, often they worry that it can get generated. Yeah, if it doesn't close.
No, it doesn't. It doesn't because it becomes free at infinity. So news operators behave free.
They just commute.
They just get very similar.
Yeah, I don't know.
One.
Yeah.
I mean, we know, for example, I can have infinite number of states and whose entropy will be the same. Right?
Yeah.
All unitaries.
Exactly. Yeah.
They will in general change correlation from.
Yes, yes, yes.
So in general, this idea that I will be able to count bonds or things crossing and that will give me everything. One would think that anything based on that will not be able to capture all this.
I agree, and that was related to Rajesh's question as well. And I don't think, I agree with you. I don't think it's ever going to give you everything. So my claim is not that random tensor networks is going to give you quantum gravity. It's more that it's giving us a picture. For first thing I can say is giving us a picture of how maybe the gravitational path integral is functioning, and secondly that it sometimes teaches us things about the gravitational path integral because of this correspondence. That's all I'm claiming.
Another thing one could say, I think, is that you could try to make the regions smaller and smaller, split them further and further,
Yes.
and try to probe it in multipart.
Though that would be the second kind of thing where you would like probe things using the random tensor network, but treating it as random, I guess, is the problem for like computing detailed things.
No, but would at least this.
It may or may not. I mean, already at that level there's a problem. Already at that level there's a problem that there's a mismatch between random tensor networks and gravity for some other quantities. So you have to be always careful when doing this translation.